As we start learning about organic chemistry, we're going to very quickly learn that functional groups become the basis for almost everything that we do. So we need to understand what a functional group is, although we also need to understand what it does for us. So a functional group basically becomes a grouping of atoms, or in some cases a bonding pattern between atoms that allows us to classify. So we kind of impose a structure on it. And it also is going to influence many of the chemical and physical properties. So all things that are alcohols are going to behave in a certain way and not that way. The functional group is going to also determine the nomenclature. For us, that's going to be one of the biggest things that we do with it, because we're going to have to recognize this is the functional group, so this is what I do for nomenclature. So we're going to go through some of the basic functional groups. There's going to be about 10 of them here. We're going to spend most of our time on a smaller group of them, but we're going to start with the alkanes. And the alkanes are probably the thing that isn't really a functional group, but is sort of the starting point for everything else, where we only have carbon and hydrogen atoms in that thing, so they're sometimes called the hydrocarbons. And all of the carbons are going to be single bonded to each other. So the most basic of ones is carbon with 4 hydrogens, which isn't really an alkane, I guess you could say, because there's no carbon-carbon single bond, but that's the one that's our starting point. Now we would often write that as CH4, but we can't really see the alkaneness of that compound when we write it like that. If I look at a longer chain of carbon atoms with some branching and things like that, then I end up with this, and then I can see the carbon-carbon single bonds. The one on the right there is a little bit better representation than some of the other things we could do. Like, I really wouldn't call that C6H14, because that doesn't give me very much information. I would write it out in this longer form. I don't necessarily need to show all of the bonds, and I don't necessarily need to draw it in a zigzaggy fashion like that, but also understand that the hydrogens attached to each carbon look a little bit like the first one, where they are also single bonded to the carbons. But because that becomes a very complex, large picture, we start to compress it into the CH3CH business. Every carbon is going to have 4 bonds, so as we draw these things, that becomes a pretty important piece. I can also have these things wrap around and form a ring, where one end bites its own tail or something like that. And that becomes another story, which we can tell some other time. But the same rules would apply. Carbons are single bonded to each other. Hydrogen sort of fills in the remaining of the 4 bonds that each carbon must have. Alkene is the next functional group up. It's not a different kind of atom. It's still carbon and hydrogen, so it's still a hydrocarbon, but now the carbons have at least one, the carbon chain I should say, has at least one carbon-carbon double bond. And that, what I've written there, is a carbon-carbon double bond, not carbon equals carbon, because while that's true, it doesn't really make a lot of sense. So the simplest alkene would be a 2-carbon alkene with a carbon-carbon double bond, and it can grow from there. And again, I have to, in most cases, write out a longer structure so that I can understand more about it. Like, for example, where the carbon-carbon double bond is, because here I have, in both cases, 4 carbons, 8 hydrogens, but the carbon-carbon double bond is in a different location. And I could have a much longer chain, and on this one, even though most of that thing you would say is carbon-carbon single bonds, so most of it is alkane, because of that one carbon-carbon double bond, the whole thing becomes alkene. Alkyne, we're not really going to spend a whole lot of time with, but it would have a carbon-carbon triple bond, also just carbons and hydrogens, so also a hydrocarbon. Point of trivia, a alkane, everything is carbon-carbon single bond, is sometimes called a saturated hydrocarbon. Alkynes and alkenes are sometimes called unsaturated, but carbon-carbon triple bond, and again I've got it drawn like that. Simplest one would be, again, a 2-carbon, so I can have a carbon-carbon triple bond, but the same thing going with the alkanes and alkenes, I can have longer ones that would still have, because they have the one functional group, the entire molecule is considered to be, in this case, an alkyne. To go to an alkyl halide, well, we know what the halogens are, we know what the halides are. They're the fluorine, chlorine, bromine, iodines. So as soon as I have one of those atoms on the structure, well, the whole thing is now considered to be an alkyl halide. Now, one of the problems that we're going to run into with this one is that at first glance, if I'm not looking carefully enough, that chlorine, because of the C, doesn't really stand out as a Cl, a halide, and we can sometimes think of it as something else. But again, as soon as I have one halogen atom on that structure, the whole thing is an alkyl halide. You might be wondering what happens if there was a double bond in there instead of all carbon-carbon single bonds, and the answer is we're not going to have a lot of that where we have to decide what the primary functional group is, but a little bit. And we'll talk about that another time when we have to start prioritizing functional groups. Their alcohols and ethers are often put together. We are not going to do much with ethers other than recognize them. Alcohols, we will spend time naming them and understanding their chemistry. They can sometimes be thought of as what's called an organic derivative of water, which means if I look at water, which is oxygen with two hydrogens, if I replace one of those hydrogens with a carbon group, that is now an alcohol. If I replace the other hydrogen with a carbon group, that is now an ether. They have properties very different from water, but if I were to look at the building of that molecule in terms of here's what I know about water, and then let's start replacing hydrogens with carbon groups, I can have different lengths of carbon groups on there. I can also have the alcohol group, the OH group, in a different position. So here it's right on the end where the carbon of the functional group is attached to one other carbon. That's sometimes called a primary alcohol. If that carbon of the functional group is attached to two other carbons, it's called a secondary alcohol. And this last one is called a tertiary alcohol, where the carbon of the functional group is attached to three other carbons. And why does that matter? For the most part, it doesn't. But there is some chemistry that does change. We're not going to worry about it too much, at least not yet, but that language does show up. Amines, not going to be a big thing for us, but just so you know, sometimes considered to be organic derivatives or versions of ammonia. So ammonia is nitrogen with three hydrogens, and as I start replacing hydrogens with carbon groups, I have these different types of amines. All called amines, right? We don't go from something else like we do with alcohols and ethers. I can also, what's interesting about this one is I can also have the amine kind of in the middle, or I can also have it attached on a branch, and of course I just did the reverse from what I showed you, but that's okay. We're not going to do the nomenclature of amines because if it's sort of sticking out there as a branch, I do one thing. If it's buried in the middle of a chain, I have to do something different. So the nomenclature of amines gets kind of weird. Aldehydes and ketones we will probably spend some time with. And in that case, they both contain what's called the carbonyl group. You may have heard about that if you took biology, because it shows up in certain biological molecules. You might have pronounced it differently. I'm not going to really call it a carbonyl group all that often, but that's a carbon-oxygen double bond. So if it's an aldehyde, then that carbon-oxygen double bond happens right at the very end carbon. So I've got a carbon double bond oxygen followed by a hydrogen. If I have a ketone, then that carbonyl group, that carbon double bond oxygen, is a little bit more in the middle. So if I look at the carbon-oxygen double bond, there's a carbon on one side, there's a carbon on the other side. That's the difference between a ketone and an aldehyde. And of course with a ketone, I could also do it as a ring where it's somewhere on the ring, but still carbon on either side of the carbon-oxygen double bond. Carboxylic acids, now at this point we have to look a little bit beyond what we're talking about, although sort of the main thing that stands out, which was kind of true for aldehydes and ketones as well. You may have learned about acids in some other chemistry class. These are acids. They're legitimately acids. They're organic acids. At one point you may have learned that acids are sour tasting. This is probably where that comes from, because most of the other acids that you would have learned, like hydrochloric acid, you don't really want to be tasting that stuff. Has what's called a carboxyl group. And again, I'm not really going to use that term, but the textbook does, and if you come across that somewhere else, you'll know. A carboxyl group is that carbon double bond oxygen followed by an OH group. Please don't look at it as like a carbonyl and or like a ketone or an aldehyde with an alcohol at the same time. It's the full thing is the functional group. That has to be on the end of a molecule somewhere. if I keep looking beyond that functional group, as my functional groups start to grow, I will also get one more step, and that is into an ester, where I'm not really too worried about what it's sometimes considered. Again, if you find if you find the functional group, I've got a carbon-oxygen double bond followed by an oxygen, and instead of that being an OH, that oxygen is followed by another carbon group. So the carbon chain continues, or doesn't continue, gets split up, and then there's another piece further down. Because the carbon chain is split up, again, the nomenclature of an ester is quite different. We're not really going to spend time with nomenclature of esters. You might see a few, you might see one and do a couple for a certain purpose, but not generally speaking are we going to be doing nomenclature of esters. That one can be in a chain because I can put the oxygen in the middle of the chain. So if you're looking at that thinking, well, it's kind of like a ketone with an ester, with an ether at the same time, it's not, it's an ester. Amides, that's about everything we're going to do with amide nomenclature, or with amide functional groups, is just recognize them. But a carbon double bond oxygen, speak slowly, followed by a nitrogen, followed by something, maybe hydrogen, maybe more carbons, things like that. So they can get kind of, now this last group that I had, the last row, if you took biology, you would have learned about amino acids. Now, the one that I have there on the left is not an amide because the carbon double bond oxygen is not connected to the nitrogen. That is an amine group on one side and a carboxyl group, the acid group, on the other. But if I start to link them together, get a few of those and start linking them together, now I have, well, in chemistry, several amide groups. In biology, you would call that proteins. You would start building up peptide bonds, you would start building up proteins, amino acids, forming proteins. Okay, for us right now, all we want to do is be able to recognize functional groups, but we are going to be doing more with some of them. You should be able to draw compounds given the specific functional group and a chemical formula to go with it. And then we'll see you another time.